In this lecture, we developed some simple derivatives. In part one of our course, we introduced the concept of the instantaneous rate of change, or the IRC, at a point P, and viewed it as a limit of values of the average rate of change, or the ARC, as a second point, Q, on our graph approached the point P. In general, given a function f of x, the IRC of that function at a particular point is itself a function. We're going to ask ourselves, if I plug x in, what slope do I get? This is going to give me a new function. This function, slopes of the original, is called the derivative. Given a function f of x, we define a new function, f prime of x, as follows. We're going to use the definition of the derivative, or the definition of the IRC. F prime of x is the limit, as h goes to 0, of the average rates of change. The numerator here is the change in y, and the denominator is the change in x as the point Q approaches the point P. So we have in this expression, this ratio is the average rate of change. The instantaneous rate of change, which we'll call the derivative at x, is the limit of the average rates of change. We will say notation that the derivative of f at x is f prime of x, or we'll say the IRC, or the slope of f at x, is f prime of x. Since the derivative concept is so powerful, it has been used in many different scientific fields, and there are a variety of equivalent notations for the derivative. Since the derivative is the limit of slopes, we know that f prime of x is the limit as delta x goes to 0 of this slope. The IRC is the limit of ARCs. For this reason, sometimes we write dy over dx as the IRC in place of f prime. This is to remind you that this began as a slope. So dy over dx is the limit of delta y over delta x. And our goal for the rest of this chapter is to compute this new function f prime given f. By the way, dy over dx is Leibniz notation. We will use that in the course along with the prime notation and occasionally some other notations. In lecture 1.7 of this course, we used the binomial theorem, or Pascal's triangle, to develop a formula for the derivative, or the IRC, of power functions, x squared, x cubed, x to the fourth. And we were able to see that if you start with a function x to the n, where n is a positive integer, then the derivative was n times x to the n minus 1. At a particular point x naught, the derivative was n times x naught to the n minus 1. In derivative notation, we discovered that if you give me a power function where n was a positive integer, then the derivative was nx to the n minus 1. The derivative of x squared was twice x, or if we plug in 3, twice 3 equals 6. That was an example we did earlier. A remarkable fact, which we will not prove here, is that this formula given by the binomial theorem works for any real number n. It does not have to be a positive integer. For example, suppose I have 1 divided by the square root of x, so that I can write my function as x to the minus 1/2. The derivative formula still works. The derivative is, I pull down the exponent to get minus 1/2, and then the new exponent is the old one with 1 taken away. So the new exponent is minus 3/2. So the derivative of x to the minus 1/2 is minus 1/2 times x to the minus 3/2. We can write this as a theorem, a power rule for derivatives. Suppose you give me a function x to the n, the derivative will be n x to the n minus 1. So again, here's the power rule. We might add an asterisk to this rule. Note, this rule obviously holds if the exponent n is 0. Suppose the exponent n is 0, so we're really taking the derivative of 1. If n is 0, x to the 0 is 1, but the function f of x equals 1 is just a horizontal line. So the derivative has to be equal to 0. Our formula gives this. If I take x to the 0, then I get 0x to the minus 1. Anyway, I'm going to get 0. In fact, if c is a constant, then the graph of f of x equals c is just a horizontal line, and of course it has slope 0. Now, I don't tend to state this as a separate result, but many textbooks do. So let's write this down. If my function is a constant, then its derivative is 0. In lecture 1.8, we developed the derivative, or the IRC, of some transcendental function. We did two trig functions and the exponential function. Let's write these results down. We showed that if you took sine x, its derivative was cosine x, and if you took the derivative of cosine x, you got minus sine x. We also did the derivative of the exponential function. The derivative of f of x equals e to the x. The derivative of f of x equals e to the x is, drum roll, e to the x. It doesn't change. So summary, if my function is a constant, its derivative is 0. If the function is a power on x, the derivative is n x to the n minus 1. The derivative of sine is cosine, the derivative of cosine is minus sine, and the derivative of e to the x is e to the x. With these basic derivative rules, we can compute the derivatives of lots of functions if we also have an algebra about the derivatives, and that will be developed next.